In this video, our goal is to build on the concepts earlier introduced in the first video of this unit. First of all, we consider population characteristics. Let's say our population of interest in this case is the population of all Toyota Camry cars that are currently operating on US roads. We might be interested in a characteristic of this population. What is the current proportion or fraction or percentage of all Toyota Camry cars that are currently sitting at the mechanic's workshop? Is it 50%? Is it 75%? Is it 20%? If that population proportion or population fraction is unknown, well, our interest might be to first define the unknown. So that would mean that out of the entire population, the population size, that is the whole count of all Toyota Camry cars, our capital X here will be all those currently at the workshops, at the mechanic's workshop. And we define that fraction as the population proportion. How easy is it to find this population proportion? Well, first of all, you need to be able to access all Toyota Camry cars in the United States. That can prove to be a challenge. In statistics, particularly in inferential statistics, we know that this is usually difficult. And so what we do is we usually take a sample using a sampling technique that we learned in earlier classes. We take a sample from that population, which we hope is random and representative of the general characteristics of that sample. And from that sample, we compute the sample proportion P at or P bar. And that would mean that out of the entire sample size, let's say you were able to gather about 500 Toyota Camry cars that you randomly sampled across the United States. And out of that 500, those who have the attribute of interest, that is, are currently seated at the mechanic's shop, let's say there were 300 of them. So that means our point estimate of the original unknown quantity, which is the population proportion, is our sample estimate, and that is going to be x over n, or 300 divided by 500, which will be 0.6. This value is a point estimate of the unknown population characteristic or the unknown population parameter. Now, what we're trying to learn is more about how this sample proportion varies from one sample to another, and if we can model it using the normal distribution. You see, according to the central limit theorem in statistics, we know that if n times p, if the sample size times the population proportion, if it is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10, then we can estimate that the normal distribution will be a very useful model for modeling how your p at varies from one sample to another. There are other conditions too, that the sampled values are independent, that the sample size is particularly not more than 10% of the population size. So you see, the sample proportion, we do want to make a solid note of this, which is represented as P at or P bar, is an example of a type of mean, where it adds up values ones and zeros, depending on whether a sample unit has the desired characteristic or not. To bring this home, and by this I mean the idea of sample proportion or point estimates, let's consider this example. A sample of 500 nursing applications included 60 from women. what is the population proportion in this case? That is, what is the unknown that might have possibly required that we collected this data? Well, the population proportion in this case that might be of interest, which is unknown, it might be the proportion, if you like, in regular English we call this the fraction of all nursing applications. That is the population of interest of all nursing applications, and for that population we're interested in those from women. So the proportion of all nursing applications from women. Okay, now if this is unknown and we cannot access the entire population, our best route might be to randomly take a sample from that population and find the sample proportion. The sample proportion will be out of the entire sample size. In this context, a sample of 500 was taken. How many met the characteristic of interest? The sample size is represented by lowercase n, and how many have the attribute of interest out of the sample size? The count of those who have the attribute of interest was 60 from women. So 60 out of 500, and that represents about 12% of all applications were from women as far as the sample is concerned. So in this case, this 0.12 is our sample proportion. It is also our point estimate, our best guess of the unknown population proportion of nursing applications, provided the sample is random and representative of the population. So take note that P-hat is a reasonable, the P-hat or P-bar is a reasonable estimate, and in fancy terms, I'll say it's a point estimate of the unknown population proportion P. We want to keep that in mind as we progress. Our next interest will be to see how P-hat varies from one sample to another. You'll recall earlier that in an earlier video we said that our P-hat would tend to have a normal distribution with a mean where it will average around the unknown population proportion, and the standard error of that point estimate is given by P-hat, also called the standard deviation. Now, let us delve a little bit gently into these concepts. You see, when we say that these conditions are met, we said our sampling proportion can follow a normal distribution with a mean equal to the P, which is the unknown population proportion, and the standard error is equals to P1 minus P all over N. But we do recall that this P, which is different from P-hat or P-bar, this P always comes from the population. This is the population proportion, which is usually unknown. So how can we use it in this formula? You see, when your P is unknown, the population proportion, which usually is the case, we can estimate it using the next best thing, which is the sample proportion or the fraction or percentage you got from the sample you've collected, the sample data you might have collected. So let's take an example here. Suppose you have taken a sample, and out of that sample, 24% of them have the attribute of interest. Now, that sample size was 144. Our goal is to find the sampling distribution model of the sample proportions. The first step is to check if the conditions NP greater than or equal to 10 and N1 minus P is also greater than or equal to 10. If that condition is met, then we can use a normal distribution which is one of the standard distributions we learnt in earlier classes to model the sampling distribution of the sample proportions. So let us consider how that goes. So I'm going to draw a line here. My first step, step 1, will be to check underlying assumptions. To check underlying assumptions, I would like to check what my value of NP is. My N is the sample size, which is 144, multiplied by P. Our P is unknown. According to what we learned earlier, or what we established earlier, when P is unknown, we estimate that value using the known sample proportion. So I'm going to replace this with P at. Rather, let me write this way. Sorry. Let's estimate this as N is known, so we keep N as is. P is unknown. We estimate it using P at. So that will be N, which is 144, multiplied by the sample proportion, 0.24. And that will give us about 34.56, which exceeds 10. We like that. So I'm going to put a check mark on that. Also, N times 1 minus P, that will be N times 1 minus P at, that will be 144 multiplied by 1 minus 0.24. That will be equal to 109.44, which also exceeds what? 10. So both values must be at least 10. And because they are both at least 10, we can say that P at follows a normal distribution with a mean of P, which if it's unknown, we estimate it using P at, and the standard error is P at 1 minus P at all over N, replacing all instances of P with P at. And so that would be that we're dealing with a normal distribution where the mean of the sampling distribution of P at is equal to P at, and P at is 0.24 here, according to the question. Okay, and then next we need the standard error. That will be P at 1 minus P at all over N, same as the square root of what? 0.24 multiplied by 1 minus 0.24 all over 144, which will give 0.0356. So step 2, the final step, would be that the sampling distribution, according to the question, we have to find the sampling distribution model. So the sampling distribution model of the sample proportion P at or P bar, whichever one, follows a normal distribution model. Since the conditions we checked earlier were satisfied, normal distribution model follows a normal distribution model with the P at following a normal distribution. Mu of P at is, what value did we get? 0.24, and a standard error or standard deviation of let's not write the formula again, of what did we get? 0.0356. Note that with these parameters given, it is possible to compute probabilities associated with P at. We'll see that in later examples. So here we go to another example. And this example says that according to a survey in a country, 22% of adults in that country do not own a credit card. Suppose a simple random sample of 300 adults is obtained. Why would they do that? They are trying to possibly confirm if that 22% holds true. So we are trying to be skeptical statisticians, which is a very healthy way to approach claims that are made in everyday life. No doubt about it. So This is the hypothesized proportion. So this P is said to be what? 22% or 0.22. Is it valid? I don't know. Or the only way to check is to collect a sample data from 300 adults. And based on this information, we'd like to complete parts A through D below. Okay? Question A, we are to describe the sampling distribution of the sample proportion, and that will be the sample proportion of adults who do not own a credit card. The first step would be to check what? Conditions. And to check conditions, we like the condition of independence, and that pertains to what we learned earlier. We like the sample what values to be independent. We like the sample size to be no more than what 10% of the population size if we have the population size available. And then we like our success failure condition, okay, which we will illustrate here. So the independence here, we'll assume that adults were what? Randomly selected. So the sample is randomly drawn. And if the sample is randomly drawn, then what the views of one adult is not dependent on the views of the other adults that might be in the sample, and that guarantees the satisfaction of the independence requirement. So we assume that the sample is randomly drawn, and then two, we want to look at the success value, the success proportion, that is n times p. In this case, our sample size n is 300. Estimated what our initial guess is 0.22, and that gives us 66, which is greater than 10. Then for the failure condition, we would usually check n times 1 minus p. That will be 300 multiplied by 1 minus 0.22. That would give us 234, which is also greater than 10. With these two conditions satisfied, we can say that a normal distribution model is a reasonable estimate, is a reasonable model of sampling distribution of P-hat. And if it's a normal distribution, it should have what? Its mean in the middle, and then it should have a standard deviation or standard error, since we're talking about a point estimate here. So in this case, your mean of P-hat will be equal to P. The best guess here was 0.22 according to the question. I'm going to erase this a little bit. Okay, and the standard error will be the square root of P, 1 minus P all over N. That will be the square root of 0.22 multiplied by 1 minus 0.22 divided by the sample size, which is 300. And that will be equal to 0.0239. So, final conclusion, the sampling distribution of P-hat follows a normal distribution where the mean is 0.22 and the standard error of that sampling distribution of P-hat is 0.0239. This is the summary there. Okay. The next thing is, what is the probability that in a random sample of 300 adults, that is out of n equals 300, more than 25% do not own a credit card? In this case, we are looking at probability that proportion or percentage, the sample proportion out of the sample, that more than 25% of them. So probability that the sample proportion is more than 25%. That is the same as probability that P-hat is more than 0.25, since 25% is 0.25. Using the normal distribution we have just established, which we learned in earlier modules, we would like to find that if the mean is at 0.22 and the standard error is at 0.0239, that would be that we want to look at where the value 0.25 stands. That would be to the right of 0.22. We're interested in the area or the probability above 0.25. What is the size of this probability? That is our interest here. Using your normal probability calculator in StatCrunch, we will get this value to be equal to 0.1047. How? Let us see. So here we are in StatCrunch, and my interest is to compute the required probability. So I'm going to pull both side by side. So let's do this, and here we are. So to look at this probability here, I would like to go to Stat, and I'll go to Calculators. In particular, I'm interested in the normal distribution. So go to Normal Distribution, and my interest is to key in the mean. The mean value here is the center value, which is 0.22. Okay, so 0.22 right there. And the standard deviation or the standard error here is 0.0239. 0.0239. And our interest is to find the probability above 0.25. So above 0.25. And we'd like to compute that probability. That will give the size of the shaded area is 0.1047 to 4 decimal places. The next part of the question says we should find the probability that in a random sample of 300 that between 20 and 25% do not own a credit card. So our interest here is to look at probability that the sample proportion is between 20% and 25%, and that would be equal to looking at the mean in the middle, and we want to locate the extreme points 0.20 to somewhere here where you have 0.25. And our interest is to compute the size of the probability concentrated in between these two values. That would necessitate going into StatCrunch, click on between, and in this case, we want to keep the parameters we already have for the distribution, 0.22 and 0.0239 for the mean and standard deviation respectively, and change the endpoints to 0.20 to 0.25 and compute the required probability. That will give us a final answer of 0.6940 to 4 decimal places. The next one says, would it be unusual? The next part of the question says, would it be unusual for a random sample of 300 adults to result in 60 or fewer out of this 300 who do not own a credit card? How do we measure what's unusual? Recall in earlier discussions on probability, an unusual event for the purpose of classroom use would be any event whose probability is lesser than 5%. So in this case, if we're being asked what is unusual, we're looking at the size of the probability that the sample proportion, that is, out of this 300, that's 60, that is equal to 60, or fewer, that will mean lesser than or equal to. Would it be an unusual event? So in this case, that will be the probability that your P-at is less than 60 divided by 300. What would that be? That is 0.20. In other words, again, looking back at the normal distribution model, we're looking at the mean value, 0.22, that is the mean, and the standard error is 0.0239, and we're interested in 0.20, and we want to look at the region lesser than that value, and the probability there will be computed using going back to standard. I'm interested in the region below, so facing the left of what value? Left of 0.2, and I like to compute that. So you have 0.2013. So the probability here is 0.2013, which represents about, which represents about 20.13%. This significantly exceeds what? 5%, the threshold for an unusual event. So, would you say it is unusual? The answer would be no. No, because the probability with p at less than for this event exceeds what? Exceeds 5%. All right. With that said, in the next video, we are going to look at some application problems and see how this can be used to answer real life problems.